All right, we're going to talk about section 7.3, graphing rational functions. First, let's talk about what a rational function is. A rational function is just a rational expression, so an expression that sort of looks like a fraction. There's a numerator and a denominator. That is a function. So it can be written as f of x equals or y equals. And it's typically made up of two polynomial functions. And so just kind of in general here, we'll just write it out that it's some function p of x, which is a polynomial function, divided by some other function q of x, which is a polynomial function. Okay, that's all a rational function is. And there are lots of different kinds of rational functions. These are some of the more interesting graphs that we will analyze. But the most basic, the simplest rational function is the parent rational function, the parent function of the rational family, which is y equals 1 over x. Okay. Now, if you kind of look at this this equation or this function, if you're trying to generate the graph, what you'll see is that you can plug in a lot of different numbers in for x, and you'll get a number out the other side. So, for instance, like if you plug in x equals 2, when x equals 2, y equals 1/2. Okay, so you could plot that point on the graph. In fact, every number that you can think of will work in this function, right? It's, 1 divided by 1,000 is 1 over 1,000. Every number except for 0. When you plug in 0, you get 1 over 0. And that doesn't make any sense, right? 1 divided by 0 is a nonsensical statement. And so when we graph this, what you end up getting, and I can just show you the graph that generates it here in Desmos, you get something like this. Okay, now you could try a bunch of points if you want, but the basic thing is that as you plug in bigger and bigger numbers, you're doing 1 divided by those bigger numbers that get closer and closer to 0. So you have this behavior where the graph gets really close to these lines, but doesn't happen to cross them. These lines are called asymptotes. Okay, so this graph 1 over x looks something like this. I'm not super picky about picking points on these. I'm mainly worried that you get the asymptotes in the right spot and then get the curves in the right, kind of the right quadrants of the asymptotes, okay? Although some of these graphs will have more than one asymptote, more than one vertical and horizontal asymptote. Okay, so let's talk about, let's find the domain and range on this. So the domain, again, domain is all x values covered by the graph. That's going to be everything except for 0. So we can write this capital R here, fancy R, and then we'll write x can't be 0, so that means all real numbers except 0. Excuse me. For the range, that's going to be all real numbers. Again, this is the y values covered by the graph, so this graph will cover all y values except for 0. So we'll write y can't be 0 here. All right, and then some of the question, well, we'll get to that in a second. So this is the behavior of the most simple rational function. Okay, so let's look at some more problems. So graphing some more problems here. But before we look at the graphs, let's talk about asymptotes a little bit more. So a horizontal asymptote is a horizontal line that a graph approaches as x approaches positive or negative infinity. In other words, if we were to analyze the end behavior, which we talked about previously, the end behavior would be as x approaches infinity for this graph, for example, to the right. As x approaches infinity, y approaches 2. It gets closer and closer to 2. All right, that's a horizontal asymptote. Some students think that it's that you can't cross a horizontal asymptote. That's not actually true. You can cross it as long as the graph gets closer and closer to it as you move to the right or as you move to the left. A vertical asymptote is a vertical line in a graph that it approaches but does not cross. You can't cross a vertical asymptote because of that divide by 0 situation. Okay, so when we take a look at the graph of 6 over x plus 2, all right, and you can just put this into Desmos, and what you'll see is that this takes the graph y equals 1 over x and moves it up 2 and makes it a little bit more, let's see, it stretches it vertically is actually what happens. Okay, and so you've already got it here, and so you can see that there's going to be a vertical asymptote here at 0 and at 2. There's a horizontal asymptote. And you can get this in a couple of ways. One, sometimes it's really easy to see from the graph. You can look at the function. You can see that divide by 0 there at the divide by 0 error would occur at 0. In other words, 0 is the number that you plug in to make a denominator of 0. All right, and so you can take and, well, we'll find the domain and range in a second, but let's find the asymptotes first. So the horizontal asymptote, that occurs at y equals 2. Well, how can you tell? Well, you can look at the graph and you can see that it sort of gets closer and closer to 2 as you move to the right. You can also look at the table. So if you take and turn this into a table and you look at larger numbers for x, so we can just keep going up here, you'll see that the further you move to the right, the y values get closer and closer to 2. Okay, so that's another way that you can figure that out. All right, the vertical ones, again, vertical asymptotes happen whenever there's a divide by 0 error. So we have at x equals 0. And then if we analyze the graph for domain and range, the domain is going to be all real numbers except for 0, because all x values are going to be covered except at 0. And then the range is going to be all real numbers except for when y is 2. So everything is good here except for when y is 2. All right, these last two, you should go ahead and try graphing them, find the asymptotes, the domain and range, and see how it goes. I will show you how to do them as well. So hopefully you paused and did these. So we'll put an x minus 1 divided by 2x minus 3. Okay, so we get this graph. And then what I'm looking for here is, again, I'm trying to find the asymptotes. So if I take and turn this into a table, I'll start with the horizontal asymptotes, okay? So I'm going to look at bigger and bigger numbers for x, and I'm going to see that the graph is getting closer to 1/2. And with Desmos, it's pretty easy to just, you can click and, or tap and drag, I think. Oops, hold on. Maybe you can't. Thought you could. On the computer, you can click and drag, and it will show you what the number is getting close to. But you can see, like if you pick any of these points, that it's getting closer to 0.52, or sorry, 0.5, which is 1/2. So the horizontal asymptote is at y equals 1/2. You do need to write y equals because that indicates that it's a horizontal line. So we'll sketch that into the graph real quick. Y equals 1/2. And then where's the vertical asymptote? Where it's, well, that will happen whenever the denominator is 0. So to figure that out, we'll do a little scratch work. When is 2x minus 3 equal to 0? Okay, if we figure that out, we find the asymptote. So I'll add 3 to both sides. I get 2x equals 3. Divide by 2, I get x equals 3 over 2. That's 1/2. And so we have a vertical asymptote at 3 over 2. Sorry, that's 1.5. Excuse me, I misspoke. 1.5. So we have a vertical asymptote at x equals 3 over 2. So we'll go over 1.5. Sketch in a vertical asymptote there. And then I'm just going to sketch the curves in accordingly. Okay. Again, I'm not super worried about points. If you get the asymptotes in there, and your curves in the right spots, then you're good. Okay. Domain and range, the domain is going to be everything except 3 over 2. Range will be everything except 1/2. Right? Last one. Find the asymptotes of the domain and range of this function, 3x minus 1 and x minus 3. Let's see what we can get just by kind of looking at it. We know we're going to have vertical asymptote when the bottom is 0, when the denominator is 0. That's going to happen when x is equal to 3. So we go out to 1, 2, 3, and then put in the vertical asymptote here. We look at the graph of this function. We want 3x, let's see, minus 1, and then x minus 3. Okay, so we get, here's our graph, and if we look at the graph, we can see that there is a horizontal asymptote, obviously. And again, looking at larger and larger numbers for x, we can kind of figure out where that is. It looks like it's going to be close to 3. We move further to the right. So we have a vertical, or sorry, we'll start with horizontal. Y equals 3 for the horizontal. X equals 3 for the vertical. Okay, so y equals 3. And by the way, in your graphing calculator, you can put in larger numbers too. So like if you want to put in 1,000, 10,000, right? So you put in really huge numbers, eventually it just becomes 3. So you can see that there. So then our graph looks something like this and like this. Again, the domain here would be everything except for 3, and then the range would be everything except for 3 as well. All right. And that's it. We're just looking at graphing reciprocal functions, which are simple rational functions. In section 4, we will look at more complicated functions, but for right now, it's usually just one vertical asymptote, one horizontal asymptote, and then usually a shift, either up, down, left, or right.